Hey, YouTubers, peeps, homies. Um, there's a riddle out there called like the two-egg problem. I think is what it's often referred to, and basically it's kind of an engineering problem, but it's also basically a mathematical problem. And it says if you have a 100-story building and you only have two eggs, and a boss or a guy says, hey, um, I want you to find the lowest floor that one of your eggs will break on. The lowest floor that an egg will break on. Suppose the eggs are absolutely identical, and they're kind of special eggs. They're not going to break on the first floor. So you basically have a 100-story building, and each floor is equidistantly high from the next one. So you just go up, 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 up. So 100 floors. They want to know what's the lowest floor it'll break on, and they want you to find a method that does two things. One, it guarantees you find a solution. So whatever method you use, whatever strategy, you will find a solution. You know that for 100% certainty, and you want the method that guarantees a solution in the fewest number of drops. Okay. So that's the two conditions. So I'll just give you an example of one that would violate it. So let's say you just start on floor 80, your egg breaks. Right? Okay, well it's less than 80. So you try 70, your egg breaks. That strategy, well, maybe if you got lucky and like you try 80 and it breaks, and then you try 70 and it doesn't break, and you try 71 and it breaks, like that strategy might provide you with a solution, but it's not a guarantee. You just took a lot of gambling, and it just happened to work out. And there's a possibility that you come back and say, hey, boss, I don't know what the lowest floor is because I wasted both my eggs. So you can't do that. These are very special, expensive eggs, and you just get one shot at doing it. That's not the point of the riddle. Um, so that's the first criteria. You don't have a strategy that guarantees a solution, so that would not. And then the second criteria is that you want a strategy that guarantees it in the fewest number of drops, right? So I'll show you another strategy that will guarantee a solution, but it doesn't guarantee it in the fewest number of drops. Suppose you decide to start on floor 50. Um, and if it breaks, well, you're left with one egg. Well, what would you have to do if you only had one egg? You only have one egg. You know it broke on 50, so 50 through 100 are out. You know you have to test floors 1 through 49. You only have a single egg. What is the only method that could still meet both criteria? AKA, you can't break the egg, or AKA, you have to be sure you find a solution and do it in the fewest number of drops, which basically the first criteria kind of determines everything in this situation, the one egg situation. So what you would have to do is literally start on floor 1. If it doesn't break, go to floor 2. If it doesn't break, go to floor 3, etc., all the way to 49. That'd be the only thing left. If you even tried to skip a single floor, say you try floor 1, doesn't break, floor 2, doesn't break, floor 3, doesn't break, and let's say you want to go to floor 5, just because you're feeling bold, like, well, this egg's doing pretty good, let's just go to floor 5. But if you go to floor 5 and it breaks, you now cannot guarantee your boss what floor it breaks on, and both your eggs are gone. You say, hey, well, it either breaks on 5 or 4. Not sure which. Sorry about that. So, um, when you're down to one egg, you literally have to go systematically from the lowest floor you haven't tested and go all the way up until the egg breaks. That's the only situation left. And knowing that is what's going to help you solve the actual solution to the problem, is the fact that you know that with the first egg, when you have two, you can kind of gamble with the first one to kind of become efficient. And then the second egg, you have to do this fail-safe one by one by one method. Um, so that's the two-egg problem. There's lots of good ideas, but there's one, well, there's more than one optimal strategy technically, because I think there's like 5 different starting points that all arrive to the same conclusion. But that's beside the point. So I want to give you a moment to either pause the video or just think about it, and if you want, maybe think of some solutions that you might want to try, or I can just give you the answer. Maybe that's what you're here for. So that's what I'm going to do right now. I'm going to go ahead and start with the answer. So the way I formalize the answer is a little bit different than the way you may have heard the answer before. And that's because I like the answer to kind of make some sort of sense, um, as opposed to like when I kind of first heard this problem and I heard its solution, like I just didn't understand it. But now I have. So here's my approach to solving this problem. I said, okay, so I know if the first egg breaks, I'm down to the step by step solution. Okay? So I said, suppose there is a solution to this problem. There's a strategy that will guarantee you to have the fewest number of drops and also guarantee that you have a solution. Okay? So you can tell your boss, hey, with this strategy, I'll be done in this many drops, and you will get an answer, a for sure answer, and no other strategy can guarantee that. Other strategies may get lucky and beat it. They might try floor 70 and it breaks, and then try floor 69 and it doesn't. They might get lucky and say, hey, I got the answer in 2, but they can't guarantee it. They can't be absolutely sure it'll work, and they might just waste their eggs. Um, so so what I did is I said, okay, suppose there's an answer to that question. Let's call that answer K. All right, so the answer to what's the fewest number of drops to guarantee a solution is K. We just assign a number to it. Okay, it might be 100, might be a billion. Well, that's more floors, but whatever. It's K. Okay, we'll just say there is an answer to the question. Okay, whatever it is, there's only so many different strategies you can do. One of them will be the best, and we're saying the answer to that is K. It's K drops. So it could be 5, 6, 7, 15, 14, whatever it is. It's K. So I said, well, now that I know the answer is K, like, well, that's not knowing very much. You know the answer is some arbitrary constant you assigned. Like, yeah, well, now that I know the answer is K, I can ask myself another question. What is the highest floor I can drop my very first egg on? Okay, so let's think about that. What's the highest floor I can drop my very first egg on? Well, if I drop my first egg on, let's say, the K plus one floor, right? So if the answer was 10 drops, if I drop it on floor 11, okay, could I still guarantee it in K drops? So if the solution to the problem is K, can I start by dropping my first egg on a floor higher than K? Let's just try that out. So if I dropped it on K plus 1, if that egg breaks, that means I have to systematically go from the very first floor, floor 1, and go all the way up to K, right? Because I started on K plus 1, so now I need to test 1 through K to make sure I find my answers. That's the worst case scenario, is I have to go 1 through K to find the answer. And this is the whole point, is that you want to guarantee the answer. So you have to take the worst case scenario as the scenario that actually happened. That's how you can tell them, this is what I can guarantee it within. So like it breaks on K plus 1, and you're going to assume it takes you to have to go from 1 all the way to K tries to find that floor. Okay? Find the floor in between floor 1 and floor K plus 1, which one it breaks. But here's the problem with starting on K plus 1. If you start on K plus 1, you have to test 1 to K floors. If you test 1 to K floors, 1, 2, 3, 4, 5, 6, 7, all the way up to K, you have already done more than K drops if you're in that situation. You've tested the K plus first floor, and now you've tested floors 1 through K. Sorry, I just thought of something. Okay, I'm just going to go on, but there's something messing with me right now. I was just wondering, what if you don't have to test the floor right before K plus 1, right? You know, like, let's say if you test up to K minus 1 floors, because after you test the K minus 1 floor, if it still didn't break, and it breaks on K plus 1, okay, you still have to test the Kth floor, because you don't know if the K plus 1 is the lowest floor. Okay, cool. Yeah, so you look at this floor is 1 through k because the k plus 1 floor could be the lowest floor. Right. So you can't just go to a k minus 1 floor and be like, well, it didn't break, so it must be breaking on k. No, it could not break on k. And k plus 1 could have been the lowest floor. You just got lucky. So yeah, so to guarantee you find the lowest floor, you have to test 1 through k. But you've already used one drop on the k plus first floor. So that means you're now in a situation where you've already used k drops, because it broke, plus 1 on your first attempt. That means that you've tried k plus 1 attempts to find the answer, which is a contradiction to what we assumed. We assumed that there was an answer that could be solved in k drops. We assumed that there was some finite number, and we just called it k, that could provide an answer. But whatever that answer is, if you try a strategy that starts higher than the solution, there's a chance that you require more drops, which is a contradiction to our assumption. So whatever the answer it is, we don't know what it is, but whatever the answer happens to be, if it's 5, if it's 6, if it's a million, whatever it happens to be, we know that we cannot start higher than that floor number. So if the answer is k, you can't start on k plus 1, or k plus 2, or k plus 3, or k plus 4. You cannot start on any of those floors, because you'll contradict your assumption that you found the right answer. So let's ask ourselves the opposite question. So we know it's impossible for whatever the answer is to start higher than that floor than the answer is. The other question is, should we start below it? Right? We know we can't start above it, but should we start below k? Should we start on k minus 1, or k minus 2, or k minus 5? Is there any reason to start below it, or do we have to start below it? So, well, here's the thought on that. If you start on the kth floor, okay, you get to test up to k floors, and worst case scenario, if it breaks, you still guarantee the solution in k drops, right? So if you start on the kth floor, that's one test. If it breaks, you have k minus 1 tests to do still, 1 up to k minus 1, and plus the original, so that makes a total of k drops. So if you start on the kth floor, you get to test all those floors up to k, and you still guarantee that you're going to get it done in k drops. So there really is no point to start on the k minus 5 floor, k minus 1 floor, k minus 2 floors, is because if you start on the k minus 2 floor, if you start on the k floor, you're still going to test every floor at the k minus 2 situation test, plus 2 more. So you strictly are just gaining benefit by starting on a higher floor that still guarantees your solution in k drops. You get to test all those floors, and if it breaks or doesn't break, you still guarantee the answer in k drops. Granted, let's say you start on the k minus 5 floor, and it breaks. Well, now you're going to get it in fewer drops, potentially. Yeah, potentially then a person who started on the kth floor. Not actually for any given test, though, because for any given test, let's say there actually is a floor, you both still would have dropped 1, both would start at the beginning and then find the exact same. Okay. Well, okay. In this theoretical scenario, let's just pretend that if you started on a lower floor, you might have a chance of getting it, guaranteeing it in fewer drops, even though in real life you wouldn't, right? If there actually was an answer, you wouldn't. Whether you start on the k floor or the k minus 5 floor, in real life it's objectively better to start on the k floor. But in this weird theoretical model, right, where we're like taking all instances of possibilities at the same time, starting on the k floor is just objectively better than starting on the k minus 5th floor, even if the k minus 5th floor in this weird model theoretically might find the answer in fewer drops. So I'm going to make another video on this, but this is just me to articulate what I'm thinking. So yeah, so let's say you get it done in k minus 5 drops now total. Whereas if you had started on the K floor, you might have gotten it done in K drops. Well, that doesn't really matter. We don't care about doing better than K drops. We care about never doing worse than K drops. And the reason being is we know that whatever the optimal strategy is, it gets done in K drops. So it doesn't matter if we can get lucky. We don't want to like gamble and get lucky and get done in K minus 5 drops. We don't care about that. We only care about making sure that whatever our strategy is, we never go above K drops. So, yeah, like getting lucky doesn't matter because the optimal strategy says you're going to get done in K drops. That is the best anyone could possibly do. That's our assumption. So, if we start on floor K, we get to test everything that K minus 5 would have tested, plus the 5 more floors. Yeah, this is objectively better. You just get to test more floors, and you still guarantee that you get done in K drops. Or you could test less floors, and you may or may not be able to guarantee that you're going to get done in K drops. So more floors and still be equal to our worst case scenario to guarantee the answer. It's just objectively better. There's no downside to doing it. So there's no benefit to starting below the Kth floor. It's not possible. It'll arrive at a contradiction if you start above the Kth floor. So that leads us to one conclusion. Whatever the answer to this crazy problem is, that's the floor we start on. If the answer to the problem is 7 drops, we start on floor 7. If it's 14 drops, we start on floor 14. If it's 12 drops, we should start on floor 12. Right? You couldn't start on floor 13 because then the answer wouldn't be 12, and there's no reason or benefit to start on a floor below that. Okay. So hopefully with me on this point. So that's what we're doing. We're going to start on floor K. Now we're going to ask ourselves another question. Well, now that we know what our first drop should be, it should be on floor K, where should our second drop be? Well, if it breaks, we're in a simple situation. We just go 1 through K minus 1. We provide the person with an answer. But now we have to ask ourselves the other question. What if it doesn't break? How can I guarantee that A, I'm still going to find a solution, and B, I'm not going to take more than K drops? Well, ask ourselves, how much higher from K can we go so that we don't exceed K drops? And we're going to find a very similar argument. So if we go up K floors again, right, so we're on K, we tried it once, it doesn't break. If we go up K floors again and we drop an egg there, let's take both situations. We'll take the situation where it breaks. So didn't break on K, that's 1 drop. Doesn't break on 2K, right? That's our second drop. And now we got to test all the floors between K and 2K minus 1. Okay, because we tested floor K, so we don't need to test that again. We tested floor 2K, don't need to test that again. But all the floors in between them, which are K minus 1 floors, by the way, right? Right? Let's say the answer is like 10 and 20, it'd be 9, right? The difference would be 1 less than K. In between, number of floors in between them. But here's the problem with that. So we've used 1 drop on K, and we used 1 drop on 2K, and now we still have to test K minus 1 floors if it breaks on 2K. So what's K minus 1 plus the 1 drop we dropped on K and the 1 drop we dropped on 2K? So K minus 1 plus 2 is K plus 1, which is a contradiction to our assumption. So basically, if we do it on floor K and it doesn't break, and we do it on floor 2K and it does break, it actually is going to take us a total of K plus 1 drops to guarantee we find the solution. Which means that after on floor K, we cannot go higher than, we can't go K floors up. If we go K floors up, we're going to arrive at a potential contradiction. In fact, since we already used 1 drop, we can't go higher than K minus 1 floors up. right? Because if we go higher than k minus 1 floor up, the gap is too big, and by the time we do all the tests, we have more than k drops total. So that's the key here, is the fact that after you try floor k, well, that's a drop, and now to keep guaranteeing that we still can get it done in a total of k drops, that gap has to go down by 1. So if we went up k the first stop, next stop we have to go up only by k minus 1 because we already used a drop, and that's going to make sure that we don't exceed more than k attempts to prove this answer. If it doesn't break here, since we've already used 2 drops, we can only go up k minus 2 because we have to make the gap 2 things smaller. So that way if it breaks, we have 2 less floors to test, so we only get done. So we only take we take 2 less tries. That's the highest floor you can go to. Literally, you cannot go to any higher floor, or you're going to contradict our assumption. And there's no point to go to any lower floor for the same reason as before, where we're simply testing more floors and still guaranteeing it in the same number of drops. So we should start on floor k. We can't go higher than k minus 1, or we'll contradict our assumption. There's no point to go less than k minus 1 floors because we're simply testing less floors for no benefit. So we start on k, then we go up k minus 1, then we go up k minus 2, then we go up k minus 3, then we go up k minus 4, etc. All the way until we add those chunks, k plus going up k minus 1 plus going up k minus 2 plus going up k minus 3 equals 100. And we want to know what is the lowest number of k that could accomplish that. Right? What's the lowest value of k that will get us to 100? So the way I would recommend, instead of trying to do k plus k minus 1 plus k minus 2, you kind of think of the problem flipped, where you start with k minus k, which is 0 floors advancing, right? Whatever, it doesn't really matter. Plus k minus 1, so that's plus 1, plus k minus 2, plus 2, plus 3, plus 4, plus 5, all the way up until you find the lowest value. So 0 plus 1 is 1, 1 plus 2 is 3, 3 plus 3 is 6. 3 plus 4 is 7, 7 plus 5 is 11, etc. Not going to go on before I make a fool of myself here. All the way up to 100. And you obviously can use a quadratic equation to do that. N times n plus 1 over 2. Set that equal to 100. Solve for n. Round to the higher of the numbers, right? If it's like the answer turns out to be 13.6, well, that doesn't matter because that's not going to get us there. So can't tell them it's 13.6 drops. It's more than 13. So, and the answer is 14. Cool thing about this solution is you can apply it to any number of eggs. You can apply this strategy to any number of eggs. You can say, well, what's the 3-egg solution, or what's the 4-egg solution, or what's the 5-egg solution? I'm going to quickly go over the 3-egg solution, and then I'm going to leave you as the rest. So for the 3-egg solution, we're going to ask ourselves the same kind of question. Well, what is the optimal answer? I just called it Q for fun. Suppose Q is the fewest number of drops that you could solve the problem with 3 eggs. Okay? So that means that we ask ourselves, the next question is, what's the lowest floor, or what's the highest floor we could start on? Knowing the answer is Q. Well, what we would do is say, how many floors could the 2-egg problem, because if the 3-egg breaks, the 3rd egg, whatever we tested on, right, we have to ask ourselves, well, we're in a 2-egg situation, and we've already kind of figured out what the optimal thing, a 2-egg thing, can do. So now we ask, how many floors can the 2 eggs test in Q minus 1 drops? So we say, hey, 2 eggs, you have Q minus 1 drops. What's the most possible number of floors you can test with that? Okay? So what you end up doing is putting Q minus 1 into that n times n plus 1 over 2 equation, getting some value. And that's the number of floors it could test. However, we do one more thing. We need to add 1 to that value, because with the third egg, we're going to test 1 higher than that, and then the 2 egg situation is going to test q minus 1 drops, and then q minus 1 plus the 1 we tested with the third egg will total to q, which is our assumption is the fewest number of drops, and that will determine our starting floor. Okay? And then we'll do the same argument. Instead, we'll go up for the second drop. We'll say, well, how many floors can you test with a 2-egg problem with q minus 2 drops? Plugging q minus 2 into that equation, see what it gives us. We're going to go up q minus 2 floors with the 2-egg problem. It's not just a floor. It's not 1 for 1, because obviously with 2 eggs you get a quadratic function. So we test, well, how many floors can you go up that way? And we'll add 1 to that. And that will be our start. That'll be our next floor up. And etc., 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 etc. So then you'll see that the 3-egg solution, I think the answer was like 9, if I remember right. I don't know when I solved it. Pretty sure it's 9. It's like almost 8, but it's 9. I remember. 3-egg solution turns out to be 9. And yeah, it's essentially a sum of the 2-egg solutions equations. You sum up whatever function you have with a 2-egg solution, it's a sum of that. So it's q times q plus 1 over 2 plus 1, all that parentheses, plus q minus 1 times q minus 1 plus 1 over 2 plus 1 in parentheses, plus q minus 3 times q minus 3 plus 1 over 2, all of that plus 1 in parentheses, dot, 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 equal to number of floors. Okay? Do that summation. Get a function out of it, right? Whatever function is gotten from summing that quadratic function, that's your function for the 3-egg solution. That's the optimal, that's the maximal number of floors in the most efficient way that the 3-egg solution, 3-egg problem, can solve for the number of floors. And we'd make the same argument with the 4-egg problem now. So the 4-egg would just start with plus 1 more than whatever the 3-egg could do. So if the answer is J, we say, well, how many floors can the 3-egg problems solve in J minus 1 drops? Right? And we'll add 1 to that. And that'll be our starting floor for the 4-egg problem. Okay? And the last thing I'm going to wrap this whole video up with is let's go back to the original problem with 2 eggs and say, hey, we can frame that problem in the exact same way. We say, what is the optimal number of floors that the 1-egg problem, which goes step by step by step by step, can solve? You know, as you can see, it just raises the power, right? It starts linear, quadratic, cubic, etc. But what is the optimal number of floors that, how many floors can the 1-egg problem test in k minus 1 drops, right? Well, the 1-egg problem is just a linear function with the coefficient of 1. It's just 1 by 1. So the answer is k minus 1. That's how many it could test. And we add 1 to that. So that's where we start. So we start on 4k. How many could it test in k minus 2 drops now that we used 1? Well, it can test exactly k minus 2. And we add 1 to that. So that's how many we go up. K minus 1. So we already started on k. We went to k minus 1. Same argument. So it's a very beautiful problem. I love it. I love the fact it has an elegant answer, even though I don't really feel I express it elegantly. Hopefully most of it made sense. And maybe I'll do another video on it, but at least I'll have something out there where I could say that I expressed my understanding of the problem, and hopefully just a few more people in the world will get it, and it'll be 30 minutes
well spent. Peace out, YouTube.